Hi, welcome back to McClutchy Maths. My name is Natalie McClutchy, and today we are continuing our specialist videos on matrix equations. This is part 2 in this part of the series, and it's our very last video in our matrices playlist. In this particular video, you're going to find out how to solve 2x2 equations using matrices. We'll look at 3 worked examples, and we'll talk about geometric interpretation of solutions as well. So let's get started. Now, I'm assuming you've watched the previous video on solving equations. It's kind of key to this part of this video. This is a continuation. So we're going to consider 2 types of equations where our coefficients are a, b, c, and d, and our solutions are e and f. And we're looking to solve x and y. Now we're going to rewrite those in matrix form. In our first matrix, we're going to use the coefficients of x and y. In our second matrix, we've got a 2x1 matrix, which is our 2 solutions that we're trying to find, x and y, and e and f are the subjects of our 2 equations. And we're going to rewrite those again and let the first equation be called equation A, then equation x, and equation b. And the reason why we're giving those names is because we're going to use our rule from video 8. Okay, so we're going to put those in the form of ax equals b and then solve for equation x, which is our x and y variables, by using the inverse of a multiplied by b. So let's have a look at that, what that looks like in a worked example, because it's kind of conceptual when we're using all letter variables. So now we've got our coefficients are 4, 5, 3, and 2. So we'll put those into our first matrix A. We're solving for x and y, and the subjects of our equation are 6 and 8, and we're going to call those equations A, x, and b. Then our next step is to recall our rule, x equals the inverse of a multiplied by b. And so we're now going to start by finding the inverse of a. And to do that, we need to find the determinant as our very first step. So we're going to take our rule off our formula sheet. We're going to solve for the determinant, and we'll find that the determinant is equal to -7. Now that we've got that, we can now use our inverse matrix rule also from our formula sheet and substitute the information that we have. So we need to basically transpose matrix A. We're going to switch 4 and 2 around, and we're going to make C and B negative numbers. Now you'll notice that our determinant of A is 1/7, and it's a negative number. So what we're actually going to do is make the determinant inverse into a positive fraction, 1/7, and we'll just change all of the numbers inside the matrix to negative numbers, and that'll make things a little bit easier down the track because it's a scalar multiplication, so we can actually do that. Now our next step is we're going to just leave it in that form. It's very tempting to keep performing the scalar multiplication and multiply it all out. But then when we're doing product matrices, then we're multiplying fractions by numbers, it gets real messy. So we'll leave that scalar multiplication till the very end and just focus on product matrices first. So we're actually going to do the second 2 matrices. We're going to multiply that 2x2 matrix by the 2x1 matrix. And we know when we do product matrices, a 2x2 multiplied by a 2x1 will give us a 2x1 as our result. So let's do that now. So we're going to multiply row 1, which is -2 times +6, and then we're going to add to that 5 times 8, which is 40, and that will make our first part of that final matrix there, which will be our first element, will be 28. And then we're going to multiply row 2 by column 1. So that will be 3 times 6 plus -4 times 8. So then that will end up being 18 take away 32, which is -14. So now we can perform our scalar multiplication by multiplying both by 1/7. You can see why I left that to the end. It makes it so much easier. So 1/7 of 28 is going to be 4, and 1/7 of -14 is -2. So that was a lot easier than trying to multiply all these numbers by fractions. Okay, so now we can say that our solution is x is equal to 4 and y is equal to -2. And we've actually solved simultaneous equations using matrices. Okay, we've also got some ways that we can interpret this using graphs. Now, you would recall from probably grade 7 that when we graph a linear equation, it makes a straight line. No brainer. Okay, and when we solve simultaneous equations, 2 lines, that point of intersection where they both cross over one another is the solution to the simultaneous equations, because at that particular point we have a single x coordinate and a single y coordinate that will solve both equations. in this case, we have what's called one unique solution to both those simultaneous equations. And so this occurs when our determinant is not equal to 0. You'll recall that when we're solving those using matrices, that if we have a determinant that's equal to 0, we end up with 0 being our denominator, and that just won't work. So this is situations where the determinant is not going to be the number 0, because otherwise our result will be undefined. And in those cases, when the determinant is 0, we have no solution for two simultaneous equations. And you might be thinking, well, when would that ever happen? Well, it happens when we have parallel lines. They'll have the same gradient, and therefore they will never intersect, and therefore there is no solution for two equations. And we've got an example here, y equals 3x plus 2 and y equals 3x plus 4. They're never going to cross, so they will never have a unique solution, which means their determinant is 0. You also have situations where you've got two equations which are basically the same equation, and that happens when one of the equations gets multiplied by a factor. So I've done it very simply here, y equals 2x plus 4, and then I've multiplied all of the variables in the equation by 2, and so we've virtually got the same equation. Now that means when we graph those two equations, they are going to overlap, and you'll end up with what looks like one line, and there'll be infinite solutions to those two equations. So there'll be infinite number of x and y values that will make sense. Okay, so let's solve now and interpret using our geometric interpretation that we've just talked about. So I've got two equations here, and firstly we'll start off by solving it using matrices, just like we've done in worked example 1. I'm going to move through this example a little bit quicker because now you know the process. So we've set that up into our forms of A, X, and B, and we are going to go on and solve now for X by finding the determinant of matrix A. So I use my formula again, and I'm going to work out that the determinant in this case is 0. So we've just talked about what that actually means for us in real life. These two lines are going to be parallel lines. So therefore there's going to be no unique solution. We can't find solutions for X and Y. Now that also means that matrix A is a singular matrix, and we learned about that a couple of videos back. Okay, so we can also show this graphically. And what that means is we're going to basically put those equations into the same form, y equals mx plus c, which will make it much easier for us to graph them. We're going to transpose those and demonstrate that they've both got the same gradient. So with that first equation, if we transpose that equation, getting y all by itself, we'll find the gradient of x is 3 over 2, or 1.5. Let's do the same with the other equation. So if we transpose that and make y the subject, we'll find in this case that the gradient of x will be 6 over 4, but we know we can actually simplify that. It'll be actually 3 over 2, x take away 5 over 2. So we've now demonstrated that they've got the same gradient, so therefore they are going to have no unique solution. They are parallel lines, and it would look like this if we graphed it. So worked example 2, Dunsky. Okay, let's look at something a little bit more complicated. You're going to see this in your textbooks, possibly in exam questions. We're asked for all of the values, possible values of z, where the equations will have a unique solution. So what it means by a unique solution is that those two lines are not going to be parallel, they're actually going to intersect. And what are all the possible values of z that would make those have a unique solution? So firstly, we're going to rewrite those as matrix equations. Just like we did in our earlier video, it looks a little bit more complicated because now we've got this third variable z, but we're not going to panic about that. Okay, so now we're going to find the determinant of A using our matrix A. So use our formula again, we break that down, and what we end up with here is what looks like it's going to start to be a quadratic. Okay, so we've got this quadratic here, and you might be thinking, where are we going with this? And why am I finding the values of z? It's not going to solve, I'm not going to get a number, how am I going to know? Just bear with me here. So let's actually factorize this particular quadratic equation. We'll take -1 out the front as our common factor, and we've got z squared plus z take away 30, and we know when we factorize that using our knowledge from prior years, we're going to have negative, and then in brackets z take away 6, z plus 5. Now at the same point, we still can't work out what the determinant is. However, if we set the determinant to equal 0, we would know the point where both of these lines become parallel lines and that there will be no solution. So let's let our determinant equal 0 first of all. And we're going to use our null factor law to actually solve for the two values of z where our determinant will be 0. And that will be z equals -6 and +5. So at these two particular values, there will be no unique solution because the two lines will become parallel. So what that means is, when we interpret that, is that as long as z is not equal to -6 or +5, then we will have an infinite number of solutions for having a unique solution, except at those 2 points. At those two values of z, we're going to end up with parallel lines. But any other value for z, we will have unique solutions. Well, that's all we've got time for today. Thank you so much for joining me, and I'd like to welcome all of the new subscribers to the channel. Lots more than this. This is just the ones that I was able to list on one page. Welcome to you, and welcome to anyone who's returning again. And if you would like to subscribe, tell a friend about the channel. If you found it helpful, hit that notifications button. And also you can follow McClutchy Maths on Facebook and Instagram. Or if you've got any questions, just contact us via email, mcclutchymaths@yahoo.com. Please do stay in touch. We love hearing your feedback here. It really makes it worthwhile for us. Well, I'm Natalie McClutchy. You've been watching McClutchy Maths. Have a wonderful day.